Okay, so this example now requires us to go back to last year and look at our identities. Now, I don't think they're on the formula sheet for this year, so this one's a bit hard unless you were given the formulas. So you're not expected to know this, but last year you had a formula that said sine of A plus B was sine A cos B plus cos A sine B. Alright? So this is really what this looks like. It looks like this, doesn't it? Where A is 4x and B is 3x. In fact, it's the exact same thing. So this expression here is really sine of 4x plus 3x, okay? Which is actually just sine of 7x. So rather than thinking the antiderivative of this stuff here, which is, I can't think of a way to do that, this whole antiderivative is just the integral, the antiderivative of sine 7x dx, which is a real easy one, isn't it? Negative 1/7 cos 7x plus c. That's it. Okay, here's a question in context now. This is an example of what we call simple harmonic motion, and there's so many things that undergo what we call simple harmonic motion, where the acceleration is proportional to the distance that an object is away from the mean point or the middle point. So if you think of like a pendulum swinging, it gets faster and faster and faster as it goes through the middle point, and then it slows down. The acceleration is always acting towards the middle point. If you think about a spring does the same thing. As it gets further away from the center, the acceleration is acting back towards the center, so eventually it stops and comes whizzing back and then goes bounce. So this kind of harmonic motion, simple harmonic motion, is a really important application of these trig functions. And this is one kind of example here. We're given the acceleration of this particle, given this trig function, in centimeters per second squared. We've got the initial velocity, and initially means when t is equal to 0, and the particle is 3 centimeters to the left of the origin, which means that the displacement is -3, and we want to find its exact position after pi seconds. So if we've got the acceleration, how do we find out what the velocity is? And we've already worked out, we already know the relationship between displacement or distance, velocity and acceleration. So if we've got distance, velocity, acceleration. We know that velocity is the rate of change of the distance, and acceleration is just the rate of change of velocity. So to go from one to the other, you just differentiate. To go backwards, say if we're given the acceleration and we want to get the velocity, we have to anti-differentiate. If we've got the velocity and we want to go back to get the distance covered, we need to anti-differentiate. All right, so the velocity here is just the integral of -9 sine 3t with respect to t. Okay, we just do the integral. So let's do this. We know the integral of sine is going to be negative cos. So let's use our techniques. Leave the -9 out there. The integral of sine of 3t is going to be -1/3 cos 3t plus c. And if we tidy that up, that gives us 3 cos 3t plus c. And again, differentiate that to make sure that you've done that right. Negative cos becomes negative sine 3t times 3, -9, and you'll see you get the right answer. Okay, so that's the velocity. Now we're told that the initial velocity is 5 centimeters a second. So when t is equal to 0, v is equal to 5. Okay, so that then tells us, remember cos of 0 is 1. It gives us this. So that tells us that c is equal to 2. So now we've got an expression for the velocity. The velocity is 3 cos 3t plus 2. Great. Now we want to know the position of the particle. That's what this question is really asking us, the exact position of the particle. So we can work out the position of the particle at any time here. We just need to do another step, which is integrate this one. So the distance that the particle travelled is the integral 3 cos 3t plus 2 with respect to time. Okay, so now the integral of 3 cos 3t. Again, I'm going to kind of chuck the 3 out. The integral of cos of 3t is going to be a third sine 3t. And the integral of 2 with respect to t is just 2t plus c. Okay, this is the expression for the distance. So sine of 3t plus 2t plus c. And again, if we go to the question, the particle is 3 centimetres to the left of the origin initially. So when t is equal to 0, distance is -2. So if you've got this is 0, 2 metres to the left, we say that the displacement is -2. So that tells us that c must be equal to -2 because sine of 0 is 0, 2 times 0, so c is equal to -2. So d is equal to sine of 3t plus 2t minus 2. Great. So now, where is the particle at pi seconds? I could ask, where's the particle at 3 seconds, 2 seconds? This tells us where exactly the particle is. But the question says at pi seconds. It's 2 pi minus 2. That's where the particle is. Sine of 3 pi, that's 2 pi, that's 3 pi. Okay, so it's just the same as sine of pi. So on your unit circle, remember, the sine values are the ones on the y-axis. So sine of 3 pi is equal to 0. So the particle is at 2 pi minus 2 centimetres from the origin. So 2 pi is about 6.28 minus 2. So it's about 4.28 centimetres to the right in this case. Okay, so here's the last question in this video now, applying integration to finding areas and with trig functions. So let's say if we wanted to know what's the area between these two curves between 0 and pi over 2, for example. Okay, so you can see along the bottom axis here, this is radians. So this actually is pi here, and this part here is pi over 2. Okay, so if we just focus on this part of the graph, first of all, working out the equations is a really good thing we should be able to do. I reckon the blue curve is just y equals cos of x. It's repeating once in 2 pi. Here's 2 pi over here. And its amplitude is 1, so that's cos of x. The red graph is sine of x, but it's repeating twice, so it's sine of 2x. Okay, sine of 2x, so it repeats twice in 2 pi. So we want to know what is this area here, trapped between the curves between 0 and pi over 2. Okay, so the integral gives us the area. So it would be between pi over 2 and 0. And we want one function minus the other. Remember, the area between two curves is one minus the other. So sine of 2x minus cos of x dx. Now, remember, you've got to do this right. If you were to do this without a calculator, you would have to work out cos of x minus sine of 2x between this point here and 0, which will give you a positive answer. And then work out the integral from pi over 2 to this point here with sine 2x minus cos x. To overcome all of that, what do we do on our calculators? We just put these absolute value signs. And then we don't have to worry about which function is on top and which function is on the bottom. Otherwise, this problem will have to be a lot trickier. You'd have to do one part sine 2x minus cos x, one part cos x minus sine 2x. So it's easy to just put those on. That's what you put on your calculator and you would get the right answer. However, remember in the exam you'd also have to actually work out the integral. So, the integral of sine 2x would be -1/2 cos 2x. The integral of cos x is sine of x. Okay, between pi over 2 and 0. Something like that. And then if you just wrote down the answer to that question, that would be fine. You've done the integration, you've used your calculator. Your calculator could also, drawing these graphs on your calculator would also really help because you could see which graph is on top, etc.